All right, so welcome back. Today we're going to talk about inverse functions. So what's the idea here is that a function f of x, it takes the x and it does something to x, right? And so an inverse function is going to be a function that'll undo whatever f had done to x. So let's get into some jargon here. First, our function needs to satisfy a certain property in order for it to have an inverse function everywhere. And that is this notion of being one-to-one. So we say a function is one-to-one, f of x is one-to-one, if whenever we have seemingly two different x values, x1 and x2, that have the same function value, then it must actually be the case that those two x values are just the same x value. You can kind of turn this around. I think maybe a more reasonable way to think about it that's the same is to say that if you have two actually distinct x values, x1 and x2, then the function f evaluates to two distinct y values at those two. So if x1 doesn't equal x2, then f of x1 doesn't equal f of x2. So we're going to get a nice test for this, but first let's just do a couple of examples. So example 1 here gives us a function f that's just listed as 3 ordered pairs. And so from there we can read off that f of 3 is 2, f of 5 is 8, and f of minus 1 is also 8. Oh, but 5 does not equal minus 1, but f of 5 and f of minus 1 are both equal to 8. So this is an example of a function that is not one-to-one. Okay. This guy g is the function, it's again just a set of 3 ordered pairs. So all we know is g of minus 5 is 3, g of 9 is 2, and g of 0 is 15. And from there I see, 3 distinct x values and 3 distinct y values. So for this one we can say, yes, g is one-to-one. And so I'm getting a little bit ahead of myself now. But the idea of having an inverse function would be a function that takes 3 back to negative 5, and takes 2 back to 9, and takes 15 back to 0. Notice that we can't have that up here. We could take 2 back to 3, but then it's unclear where we would take 8 back to. Would we take it to 5 or would we take it to minus 1? Well, for this reason, a function needs to be one-to-one to have an inverse. Okay, but what's the test? Because we're normally not given these functions that are just a finite collection of ordered pairs. We normally have functions whose domain is a lot of, if not all of, the real line. So how do we test? So let's graph f of x, y equals to f of x in the xy plane. And then if a horizontal line crosses that graph in more than one place, then f is not one-to-one. So they call this the horizontal line test. It's analogous to the vertical line test, right? For determining if we have the graph of a function. So, and I mean, the definition here too is very similar, where we just interchange the roles of x and y, right? So let's look at some graphs here and determine if they are one-to-one graphs or not. So this first example looks like I've drawn this horizontal line at height y equals 1, and it looks like it's crossing through the graph there 3 times. So this graph is not one-to-one. Notice, right, f of minus 1 is 1, and f of 1 is also 1, and f of, 3 also looks like it's equal to 1. So there's 3 different x values that correspond to the same y value. That's no good. Okay, this next one, though, looks like it's fine. I've drawn a couple of horizontal lines here, and it looks like no other horizontal line I might draw is going to cross this more than once, right? This looks like the graph of a line. So this one is one-to-one. Okay, I think the next one's going to be a non-example down here. Oh, right, yeah. This one's definitely a non-example. Look at this horizontal line here that crosses through this graph so many times, right? So this one is clearly not one-to-one. And then this last one's worth looking at for sort of 2 reasons. So it looks like this graph is the graph of a one-to-one relation in the sense that for each y value corresponds to exactly one x value. But if you recall, this graph looks like it is not the graph of a function, right? Because there are x values that get two corresponding y values. So this graph, it looks like it, if you apply the horizontal line test, it's one-to-one. But if you apply the vertical line test, it is not actually a function. So this example is a little bit strange because we only defined one-to-one in terms of functions, but we'll just take it for what it is. I think most of everything that we're going to see for the rest of this semester is going to be a function. So this example is just here to tease our brains or something. Okay, so then what if we want to show from the formula that a function is one-to-one? Well, let's go back to the first page here and look at this first definition. Assume we have two different x values, x1 and x2, that satisfy the equation f of x1 equals to f of x2, and then deduce from that somehow that we actually have the x1 equals x2. So let's see what's going on here. So here we have f of x is 3x minus 4. So let's suppose x1 and x2 are possibly two different x values that satisfy f of x1 equals to f of x2. Well, then that means that 3x1 minus 4 equals to 3x2 minus 4. Okay, but then you can add 4 to both sides, and we get 3x1 equals to 3x2, and then we can divide both sides by 3, and voila, x1 equals to x2. So f is one-to-one. So this is how you show algebraically. How about you show graphically? Well, you could graph this line and sort of observe that by the horizontal line test, there is no horizontal line that is crossing this graph more than once, so this function is one-to-one. Okay, and now let's see, how might you show that a function is not one-to-one? This is a little bit easier. You just have to find two different x values that have the same function value. So here we have f of x is x squared. Can you think of two different numbers that square to the same number? Well, sure you can, right? We've been seeing this all along. If you have 2 and minus 2, right? These are two different numbers, but they both square to 4. How about 1 and minus 1? Or any number a and minus a, right? Or at least any non-zero number, a and minus a. Those are both distinct numbers, but f of both of them will be the same positive square. So, okay, so that's the introduction to inverse functions. When we come back in the next talk, we will see what is an inverse function, and given a function that has an inverse, how do you determine what that inverse is? So we'll see you then.